So we've learned all of the terminology relating to angles and angle measurements involving coterminal, acute, obtuse, quadrantal, all of these different names for angles and how we can describe angles in terms of either decimals or degrees, minutes, and seconds. Now, what we want to investigate at this point is how we can look at a figure and recognize when multiple angles are congruent to each other. So in doing so, we're going to see within certain triangles and with certain figures, sometimes based on certain information, we can tell that two angles have the exact same measurement. So in looking at this figure, let's assume that these two lines here, we'll call it line M and line N, okay? Let's assume that M and N are parallel lines. If these two parallel lines are cut by this other pink line, which we refer to as a transversal, okay, a line that cuts through another line, then we've got four different angles that show up on each intersection of the transversal with line M, and four that show up on the intersection of the transversal with line N. Many of these angles are congruent to each other. Congruent is just the word that we give for equal measurement. So we would say, let's say, for instance, that A is congruent to D, and we would have a reason for saying that. That's because the measurement of angle A is equal to the measurement of angle B. So I'd like to demonstrate a couple of things here and recognize that angle A is congruent to angle D, and I'd like to see why that's the case. So we talked first about supplementary angles. Notice that A and B are supplementary angles because they add up to 180 degrees. B and D are also supplementary angles because they add up to 180 degrees. But since they both share B as one of the angles, then that must imply that A and D are congruent to each other. So we can say over here that A is congruent to D because they are vertical angles. More specifically, we could also say that E is congruent to H because those are also vertical angles. So notice that they are essentially just on opposite sides of an X. And so E and H are also vertical angles. And so E is congruent to H. We can also see some other relationships as well, obviously, by just looking at the other vertical angles, B and C. Looks like B and C are vertical angles, F and G are vertical angles. And so those are going to be congruent to each other individually as well. And so we could say that B is congruent to C. And we could also see that F is congruent to G. So there were a few different relationships already based off of vertical angles. Okay, so now we'd like to look at the fact that certain ones, these purple and the green, are in fact congruent to each other. So let's look at another situation here and recognize how we can tell where certain other angles are congruent to each other. Okay, so let's take a look at what we refer to as corresponding angles. Okay, corresponding angles are angles that are in the same location based on their parallel lines. So you notice how B and F are in the top right portion of the intersection of the transversal with a parallel line. Well, because M and N are two parallel lines, and the transversal is causing the angles to be the same, B and F are in fact the same angle, okay? Or the measurements are the same. So we could see that B is congruent to F. Okay. But we could also see that there's a couple other corresponding angles. We could see that C, being in the bottom left portion of that transversal, will be congruent to G. So C is congruent to G. All right, well, that must mean that C is congruent to G because they are corresponding angles. Now we could see a few other corresponding angles. We could see that A, being in the top left, is going to be congruent to E. And likewise, D will be congruent to H. But for different reasons, and maybe I'll highlight those in a different color. D and H are congruent to each other because they are corresponding angles, while A and E are congruent to each other because they're corresponding angles. But now I'd like you to look at the fact that A and D are congruent because they're vertical angles. And E and H are congruent because they're vertical angles. So by putting all of this information together, we can actually see that A is congruent to E. A is congruent here to E. And we could see that D is congruent to H. And now look at all of the purple statements and all of the green statements. We can now say that A is congruent to D, which is congruent to E, which is congruent to H. All of them are congruent to each other. They're the exact same angle measurement. And likewise, B is congruent to C by vertical angles. But then I could see that C is congruent to G because they are corresponding angles, and G is congruent to F because they are vertical angles. So we could see already a couple of different relationships, but now we'd like to take a look at alternate interior angles. So now interior means as if we were in the floors of a building. The bottom floor and the top floor would not be considered the interior of the building. Interior would be all the floors in between. So when we refer to interior angles, we're referring to all of these angles right here. C, D, E, and F are the interior angles because they're in between the parallel lines. We could see that C is congruent to F by alternate interior angles. Now we already see down here that C and F were congruent to each other, but we had to go through a process of figuring out why. In order to figure out why before C was congruent to F, C was congruent to G by corresponding angles, and then G was congruent to F by vertical angles. So now get rid of G and realize that C and F are in fact, C and F are congruent to each other. Okay, and so the way that we describe that is that C is congruent to F by alternate interior angles. And likewise on the opposite sides of those, let's get rid of that highlighting. Okay. So we could also see that on the opposite side, D is also congruent to E. Notice that they are on opposite sides of the transversal, but they're still bounded by those two parallel lines. So it turns out that D is congruent to E as well. Which, notice, we already knew by putting together the information from the vertical angles and the corresponding angles. So now let's look at alternate exterior angles. So for alternate exterior, we need to realize that A is on the exterior or on the outside of the parallel line, but so are G and H on the opposite side. Now notice how A is an obtuse angle here. It's obtuse. Turns out that A is congruent to H on the far opposite side. Those are considered alternate exterior angles, and those are also congruent. Okay, so A is congruent to H by alternate exterior angles. And likewise, B is congruent to G, since they are on the exterior of the parallel lines and they are both those acute angles. So B is congruent to G. So we have some very important relationships, because as we start to do applications and we draw the figure and we draw the diagram, a lot of times we're not given an angle that we need, but we can interpret what the measure of that angle is based off of its location from other parallel lines and transversals. Now that we know these angle relationships, there is a really beautiful relationship between the angles that are inside of a triangle. So let's call these angles A, B, and C. Now what we should recognize is that every triangle has 3 angles inside of it. And even though this proof that we're about to do for, or rather this geometric argument, I should say, because it's not necessarily a proof, but this demonstration that we're about to look at here is going to be the same for any triangle we could have drawn. So let's take a look at what happens if we were to draw a line parallel to the base of this triangle. Now these 2 lines are parallel to each other. Because they are parallel to each other, we should be able to have a couple of intriguing little relationships between these triangles. Let's first of all recognize that this angle, okay, because it's a straight line, this angle right here is a straight angle and therefore 180 degrees. We should also recognize something important about A. A is going to be congruent to this angle right up here. And if you don't remember why, it's because they are on the interior of the parallel lines cut by this transversal. Those are alternate interior angles. Likewise, for the exact same reason, angle C is going to be the exact same value as this angle C up top, again, by alternate interior angles. So since we've just rearranged where A and C were on this figure, we should be able to recognize that adding together A plus B plus C, all of those add up together to form a 180 degree angle. But knowing what A, B, and C originally were, A, B, and C were the angles inside of the triangle. So that means that in any triangle you give, the sum of the angles inside of any triangle will always be 180 degrees. And this is an extremely important relationship that allows us to say, if we know 2 angles, let's say we know angle A and C, if all of them have to add up to 180, we should be able to just subtract from 180 to find the final angle. And this is going to be an extremely important result for trigonometry. So no matter what the shape of the triangle, the sum of the angles inside of a triangle are always 180 degrees. Now I'd like to name a few different types of triangles, a few that we've already discussed, but let's take a look at this first one right in the middle here. This is considered a right triangle, simply because it has a right angle. Now, most importantly, if this angle right here is 90 degrees, then whatever these 2 angles are here, let's call this A and B, we should realize that A and B in a right triangle are always going to be complementary. So I should recognize in this case that A plus B will always equal 90 degrees. So that's going to be a pretty helpful tool as well when we deal with right triangles, is that if we know that it's a right triangle, we already know what angle A is, we can subtract from 90 to find what angle B is. Now an acute triangle is a triangle that has all acute angles inside, while all we need in order to be an obtuse angle is one obtuse angle. Now you can't have more than one obtuse angle. And I'd like you to think about why. obtuse angles are greater than 90 degrees. So if I add together two angles that are greater than 90 degrees, I already get an answer that's more than 180, which is impossible to draw a triangle with two obtuse triangles, or two obtuse angles. So let's give that a try. There's an obtuse angle. And then let's draw another obtuse angle. No matter what, there's no way for us to actually connect those two endpoints to create a triangle. We would automatically have a four-sided figure, okay? And so now what about the names of these bottom ones, okay? So first of all, it should be pretty obvious what an equilateral triangle is. Turns out that the angles inside of the equilateral triangle are all congruent to each other, and the sides are also all congruent to each other. As for an isosceles triangle has two legs that are congruent to each other, but a third leg that's not. Now, more importantly, when you look at the opposite angles of those two sides, then this angle here, opposite this side, and this angle here, opposite this side, are also congruent to each other. However, this top one is not congruent. Okay, so that's what we refer to as an isosceles triangle. It's got two legs that are congruent to each other. And finally, any other triangle that has no equal angles, no equal sides, we refer to that as a scalene triangle. Okay, so nonetheless, any triangle that we have, we should recognize, no matter what type of triangle it is, that the sum of the angles inside will always equal 180 degrees. Now, if we're given two different triangles, in this case, we're given triangle ABC and triangle EFG. If two triangles have the exact same angles and the exact same lengths of the sides, then those two triangles are considered congruent. In other words, if I could pick up one triangle and put it directly on top of the other one and have it be the exact same size, then those two triangles are congruent to each other, okay? However, most of the time we're not going to be using the fact that two triangles are congruent to each other. We want to determine if two triangles are similar to each other. Now, in order to be similar, a couple of things have to be true here. Most importantly, in order for two triangles to be similar, their corresponding angles must be equal. So in this case, angle A should be congruent to angle E, and angle B should be congruent to angle F, and angle C should be congruent to angle G. So in that case, we can see that they are similar. But more importantly, their sides would then be proportional to each other. So if I were to look at this triangle here, this triangle, EFG, is similar to a triangle ABC because their angle measurements are the same. It's just that the side lengths are much smaller. Same thing here. This triangle is now much bigger than ABC, but it's still going to be similar because of the fact that the angles are congruent to each other, the corresponding angles. So if I was to take a look at this situation right here, we should recognize that each of these side lengths are going to be congruent to each other, okay? So let's take a look at this side. Side AB would be proportional to side EF. And if we were to look at side AC, AC would be proportional to side EG. And if we take a look at side BC, BC would be proportional to FG. So when we say proportional, that just means that when we take the ratio of two sides, each of those should give something that's very similar. Now notice that, or equal rather. So in this case right here, I'd like to go ahead and come up with a convention for labeling sides. So if side A, or I'm sorry, if angle A is this lower left-hand corner, then its opposite side is considered lowercase a. Angle B is up top, so the opposite side is considered lowercase b. And obviously over here, this would be lowercase c. This is the convention for labeling triangles in trigonometry. So that would mean that this is side E, and this is side little f, and this is side little g. So lowercase letters designate side lengths, and we could see that uppercase letters indicate angles. So with this said, this would simply mean that if I were to take the ratio of any two sides, that those ratios should be equal. So let's just look at, for instance, the ratio of A over B. Well, considering these are similar triangles, A over B is proportional to the same sides in the other triangle. So that would be that A over B is equal to E over F. Let's take some other one. Maybe we take the ratio of B over C. Well, considering these are similar triangles, B over C would equal F over G. Or if we were to take, let's say, E over G, E over G would be equivalent to A over C. So this is what we mean to be proportional, okay? The side lengths and, I'm sorry, A over C. So in similar triangles have proportional sides. Proportional, I should say corresponding sides, so that we make sure that we are taking the right sides when we are setting up a ratio. Okay, so let's take a look at how this really important idea of similar triangles can help us to solve for unknown information. Let's first recognize with these two diagrams or these two triangles that these triangles are similar. There's one thing that makes these similar: the fact that corresponding angles are equivalent. If there are two arcs and two arcs, then these two angles are equivalent here. And likewise, same thing down here, 3 arcs. So angle B is equivalent to angle F. So because they have the same exact angle measurements, their sides are proportional. So we already know what the side lengths are for this triangle. Now we'd like to figure out, if we know that this side length is 8, what must that mean the other two side lengths are going to be? Okay, so we can set up any proportion we'd like, but let's say that we want to find out what side length EF is going to be. Well, we could set up a ratio of EF is to 8, as in the left triangle, 32 is to 16. Now there's a couple of ways to do this. You could just simplify this right here in order to have the same denominator as the left side. But more specifically, we would typically just cross multiply. We would recognize that EF times 16 should be equal to 32 times 8. So let's set that up. Okay, so that means that 16 times side EF is going to equal 8 times 32. Now I would typically multiply 8 times 32, but I don't want to here because I'm going to eventually have to divide by 16 anyway. And if we divide by 16, we see that side EF is going to have a particular length. 16 goes into 32 twice, so we could see that side EF is going to be 16. So we could come over here and realize that side EF is 16. If we want to find side DF, then we could do the same thing. We could set up a proportion. We could see that side DF can be found Again, by maybe saying df over 8. Now, I always like to choose the lengths that are originally given, because sometimes this will be an approximation based off of rounding. Okay, in this case it wasn't, but sometimes it is. And if you make an estimate on top of another estimate, it just becomes a worse estimate. So why don't we look at df over 8? Well, that would be equivalent to 24 over 16. Well, why don't we do it the other way as well now at this point? If we divide the numerator and denominator by 2, that gives us 12 over 8. And now we could see that the denominators are the same. So that must tell us that side df is equal to 12. Okay. Now this one was a relatively simple one because you could see here that 16 is twice as big as 8. So that means that this triangle on the left in general is twice as big as the triangle on the right. So you could have just divided each of these quantities by 2 and gotten to the answer. But it's not always as obvious, so that's why setting up the proportions is the better idea. Okay, let's do one last example as an application in order to see how this relates to application problems. It's always important to draw a diagram whenever you're dealing with an application problem. Okay, so workers must measure the height of a building flagpole. Okay, well, if we want to measure the height of a flagpole, then that must mean that we should probably draw the picture of the flagpole. But then I don't know exactly, outside of just drawing a vertical line, what I would actually draw. So let's continue. They find at the instant when the shadow of the building is 18 meters long, the shadow of the flagpole is 27 meters long. All right, well, that must mean that we need 2 triangles then. Although you don't really have to get as detailed as this, you could have just drawn triangles. I want to put in perspective exactly what's going on in this problem. So first of all, we see that there's a building, and it says that this building has cast a shadow on the ground. Now, obviously, this building has cast a shadow. And it says that the building is 10 meters high. Okay. So we see that this building is 10 meters tall here. And it says that at the instant when the shadow of the building is 18 meters long, the shadow of the flagpole is 27 meters long. Well, notice the flagpole is also casting a shadow down onto the ground. And so because of the fact that this is a shadow and the sun is at the same elevation, regardless of where we are, okay, the sun is shining right from up here somewhere and casting this shadow, hitting the top of the building and extending down onto the ground. And it's doing the exact same thing to the flagpole. So these 2 triangles are similar. We should recognize that these are both right triangles. We should recognize that the angle where it hits the ground is going to be congruent, and the angle up top is going to be congruent. So since these are similar triangles, that must mean that we should be able to set up a proportion to find the missing side length, which is the flagpole's height. So if we set up a proportion, we could see that 10 over 18 should equal F over 27, which implies that 18F is equal to 270, which means that F is equal to 270 over 18. Now again, sometimes you got to use a calculator for this. Hopefully we don't need to here. We could divide top and bottom by 9, which gives me 30 over 2, which then gives me that the flagpole must be 15 meters tall. So we used the fact that these 2 triangles had congruent angles in order to show that these are similar, and if they're similar, then their side lengths are proportional, which will now allow me to find missing side lengths.